traditional, not new membrane operation called pervaporation. Is again is an interesting process, not well applied at industrial level as reverse osmosis or nanofiltration, but growing in interest, particularly in petrochemical industry, in food industry. Pervaporation is becoming more and more familiar. And it's also interesting because in one of the examples in which, again, we will see that if we understand how it works, we also have to understand how to make membranes appropriate for this kind of separation. So it's not just the membrane that you have to use in pervaporation are just not the same that you are using in reverse osmosis or in gas separation, etc. They have to be designed for pervaporation. And it's also interesting, however, that just to contradict what I was telling before, some membrane that you are preparing for totally different final utilization, for example, nanofiltration membranes, people are realizing that today they can also utilize in some different areas as nanofiltration. Nanofiltration is one of the cases in which you can, if they don't work nicely in the process that you are supposed to have as nanofiltration, you can try to modify and utilize in pervaporation. And that is an interesting new possibility. Which are the basic principles of pervaporation? First of all, in pervaporation, as in gas separation, as in reverse osmosis, as in nanofiltration, you have to operate with asymmetric membranes. That means flux across the membranes is related to the thickness of the membrane itself. So if you want to increase the flux, you have to have a very thin membranes. Thin membranes is not easy to handle, it's not easy, they don't have good mechanical properties. So the solution to the problem, as we saw already and you will see more and more discussing how to make membranes, is to have asymmetric. Asymmetric membrane means that you have a system in which eventually part of the membranes is just a porous support, and the real membranes is the dense skin, in this case, on one of the face of your membranes. Remember that it's important to understand this, because if for any reason you make a mistakes and working on flat sheet membranes, you use the dense skin instead of the porous support, you kill your process. Not for the membrane is all the same, but kill your process because you induce much more concentration polarization phenomena, thermal polarization phenomena, and they will basically destroy the operation. In this kind of system, you are using, again, a dense membranes, and the transport mechanism is, as in reverse osmosis, as in gas separation, a solution diffusion mechanism. So the chemistry of the polymer forming your membrane has a very crucial role. Remember that we have a process in which the chemistry of the polymer is important, is controlling the selectivity. In other processes, as microfiltration, is ultrafiltration, membrane distillation, the chemistry of the polymer is much less important. The polymer, basically, what's important is the final morphology, the size of the pore, but the pore size distribution, but not the chemistry of the polymer in a first approximation. In this process, as in all the process where solubility, diffusivity is transport mechanism, on the contrary, the chemistry of the polymer is very important, because the possibility, the starting of the process is the solubilization of the penetrants in the membrane, in the polymeric phase. So if one component is very soluble and the other one is less soluble, you are inducing a selectivity that combined with the diffusivity will give you the overall final permeability of the system. So this is the kind of system we are talking about. And so pervaporation is a system, a membrane operation, in which you have permeation through the membrane from a liquid. In this case, by the way, different with gas separation, what you are talking about, having a liquid feed on one side of your membranes, and you permeate vapor across. So you just have evaporation. But you have an evaporation from a liquid feed in vapor phase combined also with the permeation across. So we have two different phenomena. One is traditional evaporation, but we will see we also have a permeation. So the two things, the two parameters together, the two phenomena together will give the overall performance of your pervaporation system. Basically, that is the key part of the story. The separation of the components is not only related to the difference in vapor pressure, as you have in traditional evaporation system, if you're just doing in distillation, it's similar, but the permeation rates, the velocity, the diffusivity across the system is also important. And that is what makes the difference between traditional evaporation and the pervaporation in this case. The schematic vision of our system, you have a liquid feed on one side of your membranes. So you have the liquid mixture that will just face the membranes and the vapor that is going across. So at the end of the story, starting from one stream, you will have two streams. One is the liquid retentate, and the other one is the vapor product across your membranes. So this is the overall, and you are assuming that the vapor pressure of the feed side has to be higher than the vapor pressure on the permeate side, otherwise you don't have any driving force across your system. What we were discussing before as basically is the transport mechanism. We have not been discussing about gas separation until now, but the transport mechanism is exactly the same that we have normally in gas separation. Solubility, diffusivity is the same mechanism that we will discuss when we will discuss about gas separation. And the driving force is the gradient of the chemical potential of the different components in the membrane phase. So that we can, the chemical potential that we learn, we can be written in terms of vapor pressure in the liquid and the vapor phase. So that is the system that we are looking for. On the permeate side, you can see you can have, to create the vapor pressure gradient, you can make a vacuum or sweep gas. Normally, in pervaporation, you may have you're using vacuum pump. So you pressurize on one side of your membranes, or you just have, you can stay atmospheric pressure, but you create a gradient by making vacuum downstream, or using a sweep gas that is removing continuously the permeate, and that will create the gradient that, and the driving force in your system. So the difference in chemical potential is the component that we just is creating the driving force in the system itself. You can operate, I was mentioning, in different way. You can have a vacuum on the permeate side, or you can also have, you can create the difference in partial pressure by using a sweeping gas on the permeate side, or you can also create a difference in temperature. There's been some confusion in the literature between pervaporation and membrane distillation. And sometimes you can find still today some paper where people are talking about a thermal pervaporation, assuming that there is something similar to membrane distillation. There is a basic difference. The transport mechanism is totally different. And in pervaporation, you are using a dense membranes, and the mechanism of transfer is solubility, diffusivity. In membrane distillation, as you learned, you are using microporous hydrophobic membranes. No liquid will penetrate, and you just have the formation of your vapor at the mouth of each pore of your membranes. So there is no difference, no similarity between pervaporation and membrane distillation. The kind of selectivity that you can have totally different origin compared to the between membrane distillation and pervaporation. But sometimes some confusion still exists. So you can have a vacuum driven pervaporation, where you just have downstream your membranes, you will have a vacuum pump that will create the vacuum. You can create it through a delta T in the system, and you will have to condense on the vapor side. And or you can create a sweeping gas driven pervaporation, nitrogen or CO2, depending what you're looking for. That is just removing continuously the vapor that is crossing your membranes, and you can condense in permeate side. So these are the different expression. If you want to correlate the mass transport with the driving force, the flux, transmembrane flux near J for the component I, will be proportional to a diffusion coefficient, as in solubility diffusivity mechanism. K will be absorption coefficient of the component I through the Henry law, or just this thermodynamic parameter. Remember, this is a function of temperature, and so when you make calculation, you have to find the K at the temperature which you are working. You cannot just change you from one temperature to the other, is another one. And that is the thickness of your membranes and the difference in the driving force, the gamma activity coefficient, the fugacity in the gas phase, and the pressure and the molar fraction in the liquid phase. So this is exactly the expression that you are already familiar. So this is basically the expression for the flux of one component across your membranes in terms of diffusivity and solubility. That can be both this parameter, by the way. In principle, you can also measure independently. So in principle, you can predict if you have a polymer, and you have been able to measure independently the K, that means the partition coefficient between one penetrant and the polymer, and the diffusivity can also be measured independently in the same polymer. You can predict if this polymer will be appropriate for a certain kind of separation that you want to perform. So in many labs, where you go in a lab where people are trying to identify new membranes, you will see a lot of becker with piece of polymer inside, stirring, and these are just experiments to predict, to measure the K of the absorption of your polymer in front of the different penetrant that can be you want to utilize. So that is a preliminary experiment that will tell you if your membranes is appropriate or not appropriate. And as we were mentioning already, when every time we were discussing about solubility, diffusivity, at the end, the permeability across your membranes of the component I is nothing more than the thermodynamic parameter, that is the K, the Henry law, if you can utilize Henry law, and the diffusivity of your system. The term SJK is nothing more than the membrane selectivity, and you can, in first approximation, just tell that your selectivity is given by the ratio of the permeability of the two components, J and K. So the one, remember that this value can be related to two different, totally different parameters. You can have a system in which what is important is the solubility. So you can have one component very soluble and the other one not soluble, or system in which, the solubility can be the same, but diffusivity is different. And both cases can be present, and they exist, the membranes in which the difference in the selectivity is related, overall is different in permeability. But permeability, there is a kinetic parameters and the thermodynamic parameters. And in some situation, one is prevalent on the other one. And that depends, that's what you can measure independently and to anticipate when you're doing these experiments. Selectivity is just a measure of the ratio of the two permeability. You can also define what is called a separation factor of the two components in your system. And in this case, the term that you have to introduce in this system is just the molar fraction of the component J in permeate side, and that means in the gas phase at the permeate side, and in the liquid phase in the feed solution, liquid state. Multiply for the ratio of the molar fraction of this component K in the permeate side and in the liquid phase. So you can just rewrite this term in terms of the chemical potential of the different components, and that will be the expression that you can have for defining what is called here separation factor. The traditional approximation you can have, if you want to operate in this kind of system and having a good separation, what you have to try to do is to have the partial pressure of the components on the permeate side as lower as possible. And this can be done to create the driving force necessary, and that can be done, as we already mentioned, using a sweeping gas, or normally the way in which normally people are working is applying a vacuum. And that is the kind of relationship that you can have at the end. And basically, this, if you have the limits of the separation in your system, is for the partial pressure downstream going to zero, we have an expression that's nothing more than the thermodynamic liquid-vapor equilibrium. That is represent basically the same level of separation that you can obtain working not using no membranes, but just in a traditional distillation. So the limit of this case is exactly what you can have having distillation instead of pervaporation. It's interesting, however, to understand why people are suggesting to use pervaporation instead of distillation. And there are different motivations, but one is very important. You know, in distillation, you know that you can separate at any level when you don't have any azeotrope. Most part of the solution that we have, 2 or 3 components, they can form azeotrope. You know what is azeotrope? Normally, in a normal system, the concentration in the vapor phase in equilibrium with the liquid phase is not the same. The vapor phase is always enriched in the component more volatile. But changing the composition of the feed solution, you can arrive in a situation, very general, it's not very special case, much more general than expected, in which the concentration in the vapor phase is exactly the same of the concentration in the liquid phase. So you cannot separate anymore. Because the separation normally was that if it's true that the vapor phase is enriched in the more volatile component, you make the separation, you condense your gas phase, and you have a liquid phase enriched in the more volatile component. And if you do this kind of operation 100 times, 1,000 times in the different plate of your distillation tower, you will separate the component of your feed solution. But if at one point, for a certain level of concentration, the concentration in the gas phase is equal to the one in the liquid phase, when you condense, you have the same composition. So you cannot separate anymore. This is called azeotrope. This is true in traditional system. That you can overcome this limit with membranes. For the membrane, for pervaporation, the problem of azeotrope does not exist, because the permeation that you can have across your membranes is becoming, you can separate using the permeation in the polymeric phase instead of the traditional phase equilibrium that you have in distillation. So that the mass transport in pervaporation is based on the same kind of equation that we will use talking about the gas separation, and basically discussed in terms of the molar fraction and the activity coefficient in the liquid phase. But what is different is that the separation factor that you have in pervaporation is not only related to the membrane, not only related to the difference in vapor pressure, but also related to the membrane properties that is just controlling the selectivity. So the total selectivity basically is related to 2 terms. Your total selectivity is related to the one component which is called the permeation selectivity, which is a function of the membrane properties. And the other, which is just the evaporation selectivity, which is the same, the extreme limit, if you're considering your feed and in traditional distillation process, basically. So basically, you have that you have always to consider these two components, permeation and evaporation, for the total selectivity of the system. And as I was mentioning before, evaporation selectivity is a thermodynamic parameters, and the permeation selectivity is related to the membrane operation. This is important because the relationship between these two can be totally different depending from the property of your membranes. Depending if you want to separate, for example, water from alcohol, or different components which can be hydrophilic or hydrophobic in your membranes. You can have a totally different behavior depending for a certain mixture, depending from the kind of membranes you are using. The permeability and the evaporation selectivity may be positive or negative, and one can be positive compared to the other one that can be negative. This is the most important diagram you have to remember, because this is telling you the story. If you just plot the fraction, for example, of ethanol in a vapor phase as a fraction of your ethanol in feed solution. Ethanol is an interesting case because one of the largest industrial application already existing of pervaporation is just the separation water-ethanol. If you want to use as an alternative to diesel or to the traditional oil products, alcohol, as you know, they are already doing in Brazil, and more biofuel are suggested, you have a problem that alcohol and water are forming an azeotrope. And they form an azeotrope around 93% of alcohol and water. So there's not too much water. But if you put this kind of, so when you produce alcohol by fermentation normally, and you can separate the alcohol from water, and to concentrate, normally you produce alcohol through fermentation with a concentration of the order of 12–14%. The microorganisms that today we can use, they die when you increase the concentration too much. So you normally are about 12–14% in alcohol, and after you have to remove as much as possible the water to arrive to a concentration approaching 99%. Any water in an engine will induce corrosion and will destroy the engine very quickly. So one of the first interests in pervaporation was just utilize this methodology to overcome the problem of the azeotrope that we have in the concentration of alcohol. And that's why you can find a lot of data in the literature of this kind. You can have two different kinds of membranes. You can have membranes, for example, as cellulose triacetate membranes, or membranes with silicon rubber. They can be hydrophilic, they can be hydrophobic. That means there are membranes in which water is moving faster than alcohol, and membranes in which water is moving slower than alcohol. And you can see here that the traditional plots will be something linear in between. What is happening is, depending from the kind of membrane, you can have a different kind of behavior. You can have a system which deviation from ideality is on this kind when you are working with silicon rubber membranes, or totally different when we are working with cellulose triacetate membranes. Both cases are industrial, and the difference in the choice between one and the other is related to the economy of the system, to the cost of the membranes, to the lifetime of your membranes, etc., etc. But you can use hydrophobic or hydrophilic, and you can remove thermodynamically, separation is all the same. But if you add your membranes, you can have this kind of behavior because one of the components is moving faster across your in the polymeric material from your membranes, or the other behavior because the same component is much slower and the other component is moving faster. So that is giving you the completely different behavior. You see here that in using a silicon rubber membranes, where with ethanol is more perm selective, or cellulose membranes where water is more selective, you can have a totally different kind of behavior. This is hydrophilic, the other one is hydrophobic. This kind of a process is today utilized in some area. It's the standard. There are no big plants, but in the pharmaceutical industry, in this cosmetic industry, if you want to produce, for example, isopropyl alcohol, or you want to recover isopropyl alcohol, which is used for the extraction of different components, or you want to produce very soft, expensive cream for ladies with acetone, basically ultra pure acetone, with no water at all to avoid any the formation of any emulsion, etc. This technology is utilized today in large scale. Most part, there are hundreds, small plants, relatively small because there are no huge production, where isopropanol or acetone are purified, are concentrated and purified from water, approaching 100% using this logic here. We understand that now the material is very important, because the material is the one that is creating, giving the benefits. If we want to overcome the azeotrope, we need a system in which one of the components has to be more soluble or more permeable, and the other one less soluble, less permeable. Remember that one term is diffusivity, the other one is just solubility, chemistry and kinetics. And many different kinds of membranes can be prepared in pervaporation. Normally, the most utilized today are polymeric membranes, asymmetric, as I was mentioning before, with a dense skin on a porous support. However, this pervaporation is one of the cases in which inorganic membranes have also been utilized. This is one of the cases in which some silicalite, some zeolite kind of membranes have been produced in Japan, but Mitsui, you can find in the little Mitsui engineering, just for large-scale application in alcohol concentration, in the dehydration of alcohol, basically. So we have polymeric membranes utilized, but also inorganic membranes, and basically this for the alcohol production. Material that you can use has to be a different kind. If you want to have a system in which you can remove water as a permeate, you will have hydrophilic membranes, and the material are polyvinyl alcohol, typical case. These are industrial membranes that in Europe, Sulzer and the PVA, and is traditionally using this. Here is not so easy because you also have a problem, this cross-link. There is one problem. If you want to separate something, and we are telling that the best separation will take place when one of the components will be solubilized in the polymeric phase. Now, solubilization very often is inducing also swelling. So if you have one component very soluble, it's so soluble that it can dissolve the membranes, basically. So you have to optimize the system to have high solubility of these components in the polymeric phase without destroying mechanical properties. That's why, in many cases, you will find this cross-link term. That means you can find a way that you can increase the amount of your permeate that can be dissolved in the system without changing mechanical properties. This is not easy. That's one of the limits of the technology, by the way, because you have to invent how to stabilize. You have to vulcanize your membranes. The same that happened with rubber in your automobile, vulcanization. In this case, it's just cross-link. So often you have some metals that you have to add to the system to create some positive mechanical properties during the solubilization. So the swelling will not destroy. So PVA is typically a good example at industrial level, but cross-linking is a very important aspect of this story. Sulfonated polysulfone, because you want to increase hydrophilic character, and sulfonation, as you learn when you're working on fuel cell, etc., is the way to increase the hydrophilic character. Polyamide, polyacrylonitrile are typical material that can be utilized as hydrophilic membranes, and basically PVA is the most present at industrial level, but also polysulfones and polyamide are also utilized. For example, the polyamide polyimide that you are using for nanofiltration membranes, in some case can become also of interest in this kind of application. Different situation when you are going to hydrophobic. You can also use polysulfone eventually, but it's not sulfonated. Polysulfone with no sulfonation has relatively more hydrophobic character than the sulfonated one. Or polypropylene, this polyether sulfone, PVDF, that has been discussed already many times, PDMS, the one that we were mentioning already, and this is the most utilized at industrial level. The same company that is producing the hydrophilic membranes is also producing hydrophobic membranes in PDMS instead than PVA. And there are some new materials, styrene, butadiene, co-styrene, ethylene, propylene, rubber, etc., that people are developing. There are a new application in which people are trying to, and that's the one that I was mentioning, no more just alcohol, that is the most traditional, but we will see a few examples of application at industrial level in the process in which new material has to be identified, having the good selectivity in terms of permeation, in terms of solubilization. And all these membranes, as I was mentioning, are normally asymmetric. Is a typical composite system. That is a PDMS with some very dense coatings on the surface. You can see here that is this PDMS, polyacrylonitrile, that is just a support, just a fabric that you can use as a polyester or any other fabric with as much as possible high porosity, so there's no mass, no resistance, no mass transfer resistant. Polyacrylonitrile is utilized for giving some mechanical properties and some better performance, but the real control, hydrophobic character, is given by a very thin coating of PDMS on the membrane surface. That's why it's typical a composite system that is the one utilized. And that's the same, the cross-section where you can see all the different layers. And again, just to mention that if this thickness will be 150 microns, the real membranes, what is really controlling the system, will be 1 or 2 microns up here. And that is the problem. That's why membranes are expensive, because if you change the thickness here, you will, using the equation that is the denominator of your relationship, and you can change 10% change of the thickness, giving a significant change in transmembrane flux. Now, to produce a system in 100,000 square meters of material per hour, and using having always through phase inversion, etc., the same level of thickness here, 1 or 2 microns, is not so obvious. You can do easily in your lab when you just carefully you check all the parameters and but if you have to do in big machine running daily and producing large quantity, if there is no problem in this no so sophisticated distribution of the layers is easy. But when you pretend to have always 1 to 2 microns dense skin, and the other has to be porous, etc., and that's the reason for which you pay $1,000 what the same polymer, polypropylene, if you just use for making more plain, costs you a few cents of $1 per kilo. If you make what is called in some things Acurel, for example, etc., costs you $100 per kilo, because it's not easy to keep the control of the final morphology of the system. I was mentioning it is a typical case in which today there's a lot of research in progress. There was research years ago. They obtained some of the results I was showing before from this company in Germany, etc., but after it was relatively quiet. Today, just because all these membrane operations are becoming more and more visible and popular for solving complicated problems, research is again active to produce new material for specific separation. This is a typical case. That is one of our patents with people from APA in Cincinnati, the Environmental Protection Agency, in which we are producing membranes by this polystyrene, block polybutadiene, block polystyrene again, SBS. And these are asymmetric SBS membrane using traditional NIPS, phase inversion at room temperature. And the necessity that we have is to try to control carefully this thickness of the dense layer, because that's the one giving the overall performance of your material. And if possible, eventually reducing as much as possible also this the other material that is used as mechanical support. And something you can make these membranes dense, or you can make asymmetric. So it's possible to handle the system during the phase inversion and to have some membranes which are decent. You can handle. That means you can make a module. You can do some real work. And in some cases, the dense ones are not so easy. The mechanical properties are much worse than the one, to the point that you must be very careful when you handle them, because you break everything. But if you know how to do it and you make this asymmetric, with a dense skin on the surface, this situation can be obtained. And you can also try to change thickness and the overall morphology. You can see that you can obtain a system with, on the dense side, on the surface side, they are basically with no porosity. This one are just defects. And the cross-section is giving you a typical asymmetric behavior. And depending from the parameters in your NIPS, depending from the concentration of the polymeric solution, depending from if you are making from the evaporation time, from the temperature of the quenching baths, etc., you can try to tunnel to change the level of the thickness of the dense skin compared to the other parameters in the system itself. And that is today is no more an art as it was years ago, where people were having the same results but learning, casting a lot of membrane, changing parameter, looking at the results, and making some phenomenological analysis at the end. Today, if you write your phase diagram for the different concentration, different temperature, and you measure your gellification point, your crystallization point, etc., you can predict how these things will change during NIPS or TIPS. What's important, if you do this, you can see here what happened. Look at this kind of experiment. When you have the same material, exactly the same story, and you make symmetric dense membranes or asymmetric dense membranes. And you can see here that if you have a thickness of 140 microns in your system, and you just plot your transmembrane flux as function of the concentration of ethanol, and here you have numbers that in terms of these units are 0.1008. And the same material in asymmetric, with a thickness in this case of 10 microns, the dense part of your membranes, is of the order of 1. So there is between these membranes and this one, there is 1 order of magnitude. But what is important, that's if you have this kind of results, and by the way, the result, that is a function obviously also of temperature. We remember that with the expression, so it is increasing with temperature, 45, 35, 25 degrees, and 45 is a reasonable temperature for most part of this, for the resistance of most part of this polymer, so you can really operate at this temperature easily, so the numbers are not bad. But what is interesting, now if you are going to measure not the permeability, but not in the transmembrane flux, but the selectivity, you have exactly for the 10 microns or the dense membranes, same selectivity, which means this is a case in which we can change the morphology of your membranes. You can change significantly, making thinner and thinner the dense skin. You can have much higher fluxes without losing nothing in terms of selectivity. Basically, we have this 3.5 here, 3.5 here. There's a small difference, but basically not influent on the overall final performance of your membranes. So that's you have to learn how to make these membranes asymmetric, dense, with a certain thickness, because you can have quite interesting selectivity eventually, and you can improve significantly the membrane flux. So same selectivity, but much different permeability. I was mentioning before that today you can find in literature more and more this possibility. If you have some membranes that you have been realizing for making nanofiltration, that means membranes in between reverse osmosis and ultrafiltration. Membrane, remember, where also the charge effects are present, the Donan phenomena, etc. But basically, nanofiltration is becoming quite interesting, important industrial application today for different reasons. In nanofiltration, what you have normally, you have basically very low rejection for monovalent salts, sodium chloride, potassium chloride, and similar, and much higher selectivity for chemical species having higher molecular weight, 100, 200 Dalton, 300 Dalton, 1000 Dalton, this order of magnitude. And this one time, membranes were only utilized for desalination, so people were looking to 99.9 for sodium chloride for big desalination plant. Today, the interest is much wider than this, and so people are looking how to separate amino acid or a lot of pharmaceutical or biological products from salts, because this is what is the final purification of different fermentation processes, etc. So more and more people are interested in nanofiltration because they can separate sodium chloride, water, solvent, etc., and concentrate the bioactive compounds. However, it's coming out that if you take some of the nanofiltration membranes, eventually not the best one, not interesting for nanofiltration, and you try to utilize them in a pervaporation mode, that means trying to separate different solvents, etc., they work nicely. So to the point that has been now, particularly this Bart van der Bruggen in Leuven University, he's just trying to also to extrapolate and to simulate, to do some modeling of how you can transform a nanofiltration membranes in a pervaporation membranes, taking the opportunity of the swelling, because nanofiltration can be too porous, too permeable if you want to use in pervaporation. But with some solvents, it's not for all this, but with some solvent, just for the property of the polymer, you can swell, because some solvents will interact with the polymeric phase, and so you swell, and this swelling is decreasing the permeability, but increasing the possibility to separate. So you can use nanofiltration membranes in pervaporation experiment, because that's the transformation with interaction with the solvent. This basically make the nanoporous structure much more dense. So you are closing the porosity and you are inducing high selectivity. So this was not, as initially was just an academic curiosity. Today is no more this. You can have you can produce a membrane that work in real separation, utilizing nanofiltration membranes interacting with some of the solvents that are present in your system and that you are interested. That's basically related to the phenomena of densification of your polymers and the disappearing of the porosity and transformation of a much better dense membrane that can be utilized in this kind of form. I was mentioning that one of the cases of interest today is one of the first case where there is no competition, basically, for inorganic membranes, just in pervaporation. This is the structure of a silicalide zeolite membranes, where Japanese have been able to realize an asymmetric, also in this case, ceramic membranes, with forming a very relatively homogeneous and non-porous layer of crystals of zeolites on your membrane, on some polymeric support. As you can see here, in this again, as we saw before, this is the overall thickness. This will be about 100 microns, so 150. The real membranes is this one, just this layer on the surface with all these crystals. That these are the one that you see here, the one less regular, but these about 5, 6 microns. There are 2 or 3, 4 microns quite dense, and the surface there is a very high level of roughness. Obviously, some crystals are not, but this is a asymmetric system with most part of the support high, very porous, and this kind of structure that is inducing interesting selectivity, alcohol water, for example, to the point that you can buy big plant from Mitsui Engineering. They did not making too much money, probably in this area, but they were suggesting huge plant just for using these membranes in the big plant for bioalcohol production, to remove all the water and to use for your engine, for avoiding to destroy your engine too quickly. So if you are looking to the possible application that we have today, I was mentioning solvent hydration is number one, and large scale is water ethanol. Isopropyl alcohol, I told you, is another interesting application, not huge plant, but many small plant in the pharmaceutical and cosmetic industry. Another interesting application running when if you are flying in winter time and you are in an airport and they are trying to, before taking the sky, you will see sometimes if it's cold outside, they have to avoid the formation of ice on the wheels of your plane. It's done with glycol. And when they just go and they just using is a lot of ethylene glycol, etc. That's to be recovered. And so after you have to treat the solution and to recover, is done with pervaporation. There are a lot of plants around where you can reconcentrate and separate water from glycol using pervaporation. This is the most industrialized application today. What is more important, and that's the area in which a lot of new activity is in progress, is the removal of VOC or separation of organic mixture. VOC, that means some dissolved organics in water, normally in very low amount, so it's very complicated to do with traditional other methodology, expensive, not very efficient. And so if, for example, in the laundry, in a lot of situations, toluene water, trichloroethylene water, methylene chloride water, and that can be done with membrane for pervaporation membranes, or that's what is becoming more and more interesting, separation of organic mixtures. That means separation of methanol, isobutane, methyl, benzene, cyclohexane, etc. Not large-scale application, at least not public, but people are working. Some other interesting industrial application, this is the one. In China, for example, they are already using dimethyl carbonate separation using pervaporation. Now, most part of this case I was mentioning are related to the fact that if you want to purify your dimethyl carbonate, normally there is an azeotrope at about 70% of methanol. That means you can purify up to a certain level, but you cannot overcome this 70%. So if you need to arrive at 90%, 95%, you have to find another system not related to the phase to the normal phase equilibrium, and that is pervaporation. And that can be, if you have the right membranes, can be done. In this case, unfortunately, if membranes able to do with high selectivity, this separation has to be stable also at a high temperature. There are people that are working in a relatively high temperature in this case, and it works. If you want to operate at the room temperature, the selectivity is not so high as expected. So still people are working and trying. We have been asked, for example, ITM colleagues are working to find better polymers to make this kind of industrial separation. This is an industrial problem. Aromatic aliphatic, another kind quite interesting in the petrochemical industry. Promanol-butanol, which is an inhibitor in different kind of operation, in fermentation particularly, how to remove continuously during the fermentation butanol, that pervaporation can just do the job. And if you are ambitious, and you want to try to do something complicated but quite interesting, benzene cyclohexane, ethanol cyclohexane, this methanol isobutane MTBE. MTBE at one moment was becoming very popular for the problem of this, new benzene, increasing the octane number and avoiding lead, this poisoning system. And that was a quite interesting alternative. And this is a case in which a lot of money has been invested, plant has been installed. Now the problem of BTE does not exist anymore in the form that was existing 15 years ago. So all the efforts, but at that moment on the Sulza that you saw is one of the industrial company producing, they were already realizing MTBE production lines using pervaporation with their kind of polymer. And again, ATBE, the same full octane enhancer used in Europe, that's another case that has been utilized. As I was mentioning, however, all these interesting, but except few cases, we wrote down 2 or 3 companies, the real problem is lack of membranes. So if you realize a nice study in your lab, and you write to pilot plant, etc., and you show now what is going on, the people come to you and you realize they have on the back huge plant, they want to separate the millions of cubic meters per year, etc., but where are the membranes? So that's an area where there is a lack of membranes, and not just membranes, but the module. When you have your membranes, it's part of the story, but you have to realize the module, and you learn that the modules are quite important, because if you don't do the module right, so if you don't well control interfacial phenomena, etc., the best membranes will not work. You will have concentration polarization, you will have fouling problem, deposition of some of the components that will kill your membranes at all. So the module, how to put the membrane, this spacer that you are using, how to promote a turbulence, how to promote backflashing, how to promote high Reynolds number on the membrane surface, which are the parameters that you can use for controlling concentration profile and fouling phenomena, etc., are very important as the membrane itself. Otherwise, we learn that what is going across is, can be exactly what you're putting in. So that is quite important, and there is not yet a lot of understanding and industrial production on this, in this area. There's a small history about by Richard Baker, who was one of the, Richard Baker has been working from a long time in pervaporation. So one time he just trying to summarize this, and that was in the starting years. By the way, pervaporation, remember, is one of the oldest operation in membranes invented 100 years ago. If you can find the evidence of pervaporation in some books published in France by Abbé Noël. Abbé Noël was, is a priest living in a monastery, and in all the monastery, they have particular care about wine. And in wine production, they observed one time, initially, that there was a big difference between when they were taking the wine in traditional barrels and blocking this barrel with candles, with traditional materials. And one day, somebody, for that is not clear why, instead of blocking with traditional system, they block these barrels using some skin of animals, basically from the intestine. And they were covering and blocking. And when they went after 1 or 2 years drinking the wine, and somebody realized that there was a big difference between the quality of the wine that was storage in traditional barrels and the one that was contained in this new barrel with this special kind of blocking. And somebody had a curiosity to try to understand what was going on. And you can find in some books of the L'Académie de France, there's a history when they give an explanation, because this natural product, this natural skin that they were using was much more permeable to water than the other system. So you have the possibility to concentrate in alcohol your wine much better than the other system. They invented the pervaporation. That was pervaporation, exactly what we are talking now. However, industrial pervaporation, not the one of Abbé Noël, has been invented a little bit later, And the first study started in the 60s, in the same period of reverse osmosis. And only in the 1780, something the GFT was in Germany, and the same that as Sulzer, they started to produce some commercial, as I was mentioning, for alcohol hydration, because that was the big problem at that time. And that was the easiest membranes, where hydrophilic, with everything, the water was going through, and you were concentrating the alcohol. But this system is going, and now the new area, the most interesting, where most part of the new application are attracting attention, is this one. Now, this is the first plant where you can remove, using the same concept, VOC from water or also from a vapor phase. You heard the story, everybody is familiar with the story of PVC. PVC, when you produce PVC, the monomer, the vinyl chloride monomer is quite dangerous, inducing disease and cancer, etc. You can find today in Europe, in China, I don't know if also here in Korea, a plant installed where you can, when you just produce PVC, all the monomer that were going vapor phase in this case can be, that is a kind of pervaporation applied to vapors, can be utilized to remove the monomers left in the air, the one producing contamination, etc., or disease, and send back again in the process. And if you do this in a few months, you pay back the investment, not because you have a cleaner air, but because you just reuse the monomers. And the monomers in this case are quite expensive. So now the reuse of monomer of different this production, vinyl chloride and some other complicated and very, very dangerous for your health monomers, are just utilized in very similar plants that in some cases are from water, or they can be from liquid phase or gas phase. And these are basically a kind of pervaporation. This is the one that are more and more utilized. This is the synthesis of methyl ester for the extraction, to extract methanol and increasing the productivity. And again, Sulzer, as you see, is a very active compound. But this is the, in perspective, what can be done, which is much more than what has been done until now. That's why we are talking now, because there will be more and more interest and growing activity in this methanol, in this pervaporation. So you can use hydrophilic, we learn, and organophilic, and you can just have, when you are using hydrophilic, that's basically you want to separate water, but you can use hydrophobic pervaporation or organophilic pervaporation, where you can extract organics from water or organic from organics. And that is the most challenging today. Very complicated because it's not easy, there are no alternative easy, and in some cases this is becoming a problem, more and more sophisticated problem, still in part unknown, because today in the air there's a lot of people are much more careful about the water than what happens in the air, and these are systems in which there is a lot of interest in liquid phase and also in vapor phase. And some of these possibilities are listed here. You will find this, and that's the one we're talking about. And just this, as I was mentioning already, the production of isopropyl ethanol is one of the typical cases which we already have industrial possibility. Another one interesting is the extraction of phenol. Phenol is big contaminant. In some cases, very stainless steel company and some other kind of industrial production are producing phenol, not easy to separate. Pervaporation is just doing some case. In some, you see here, in some case also for ourselves, there is not easy to have information. We still, normally, we know everything what is going at academic level. Here, all people don't give you any information about the kind of membrane they are using, because these separations are quite challenging, are quite interesting, and everything is still, as much as possible, confidential. How the system works, if you are not an expert, you cannot separate one unit from the other, and I was mentioning, basically you can utilize. By the way, very often today, you will find system which are integrated between one technology and the other one. This typical case very much on the study in which distillation, we learned before that you can operate with distillation easily sometimes. It's traditional, the plant already exists. However, at one point you approach azeotropic concentration, and azeotropic concentration, distillation stop working. There's no more. So in this case, what is done, instead of canceling distillation, you just operate with distillation at the best. For example, you arrive 80%, etc. Azeotrope is 90 to 92 if it's water alcohol. And you start to operate the pervaporation on the concentrate. So this kind of units integrate and overcome the limits of the more traditional unit operation. We as membrane engineers, we have the ambition to cancel this system and doing everything with pervaporation. However, sometimes it's not convenient. It can be much more convenient to integrate the two cases and just you introduce the new operation where there is a limit. This 80% thermodynamics telling you that you cannot do nothing better. If you want to arrive 99.5, you can integrate, you can operate your pervaporation on the concentrate produced from the traditional distillation towers. And that's something that more and more is going. And you can find also data in the literature telling you interesting selectivity, 200 for example, lifetime 4 years. In this case, not too big, you see 5 modules in series, that means relatively is a pilot plant in some case, or for a traditional size. But if you are in a pharmaceutical company, in a company producing a sophisticated cream for ladies, etc., this is the size they need, and it works very nicely, and as you can do. But more and more, these are becoming popular. I was mentioning about inorganic. You have the same case as Fuji, and you can have different kind, by the way, of zeolites that you can use. So that is still an area that today is starting again. We are working, for example, on zeolite membranes in petrochemical industry for some separation. And with the sponsor from the Middle East that they need to redesign their petrochemical production. And there are hundreds or tens of different separation in which having one of these units working at industrial, at economic price is interesting. So you can have a specific zeolite, you can have Fauchazite type, X and Y, you can have LTA, you can have zeolite 1, zeolite 5, etc. You know what zeolites are systems in which the selectivity is very much related also to the sieving effect, because the windows, the size, the external size of the crystals is very, very regular. And so you can have very high selectivity depending to the not possibility to penetrate in the crystal, and also desorption phenomena on the overall porosity. So this kind of system is becoming popular, and you can see here again that the surface of these inorganic zeolite membranes is quite interesting, very well done, homogeneous, no defects, and that's why the Mitsui has been, here it is, Mitsui Engineering and Shipbuilding, and they're apparently nothing to do with membranes, but now they're the one that have been synthesized by hydrothermal synthesis, and the plant at the end are quite a relatively large plant. And these are just for the production of, this is the 5 modules I showed before. These are 125 big tube installed, that means real industrial application. And they are not only Mitsui, more than one, but not too many in any case. It's interesting also the problem with the methanol. And you can have here some comparison in principle of the cost of different traditional extraction, distillation, and pervaporation. And in principle here, in terms of the cost, if you compare investment, the fixed operating cost, and the variable running cost, basically you see here that the pervaporation is at the moment more expensive in terms of investment, because there are membranes are still expensive and the system are not very well optimized. But in terms of what is important, the final costs are lower, and the variable the running cost, that means the money you have to spend day by day, which is the most important, is significantly lower than the running cost of the alternative. And that is what makes the real difference. If you don't have the money, you don't make an investment, but if you make the investment, you want to pay back. And this kind of number here telling you that in 1 year, 1 year and a half, you pay back the investment, and after you just go with your interesting results. For what concern the problem of VOC, that is the area more interesting for different reasons. One is for pollution in the air, and more industrial pollution exists. Second, unfortunately, is also for military application. I was mentioning already today, if you have a tank in a contaminated area, tank stay, or soldiers in troops somewhere, they cannot stay with the existing methodology today more than 24 hours, 48 hours, give number invented, because this presence of this biological attack or chemical effect, etc., you have to purify the air, and the system that exists give you lifetime with the portable one or the one of the tanks, no more than a certain numbers. There's a lot of interest, unfortunately, and a lot of money going to systems to realize new membranes. And in the army, they don't know, money is not a problem normally. They just, we have a lot of problem in other area, but not in the army. And they just try to make these 24 hours, 60 hours, or instead of 1 day, 2 months. If you're able to do this, you have a lot of success. For doing this, you have to find new membranes that can operate and can remove these contaminants that you can have in the air, these nervina gases, etc., and to separate from air. So that's membranes similar to PDMS. These compounds are normally present in a very, very low amount. So the best is to have a system in which you can remove them. You don't filter the air. You have to remove the contaminants, which are few ppm. So if you have a very selective material that can do the job, you can have quite interesting contracts and to develop this kind of system for the VOC removal at very low numbers. Here is a 50 or under 50 ppm, but sometimes you have a concentration factor that is to be very, very high. But quite interesting, scientifically very, very interesting system. The motivation are less important. And you see here, there are people working with different kind of material and different kind of VOC with selectivity that can be in some case quite interesting. These are the one approaching the request. Higher than 10,000, 5,000, that is our membrane. That's why we were working with, in the United States, with EPA, because in some case, for some VOC, our SBS asymmetric membranes were giving quite interesting selectivity. So in principle, the Americans were quite interested to do these kind of things for some of these biological attack and similar. Again, in real life, and not in the army, membranes are also quite interesting for some application where they are already used, and that's much more interesting. This is a typical process, integrated process for the production of high concentrate juice. Juice means also wine, by the way. It can be Chardonnay, can be Cabernet Sauvignon, produced in Australia in a place called Mildura, and exported in Europe at the end. And they are drinking beer in Australia, not wine. But if you go in some of this place north of Melbourne, in Mildura, it's about 3,000 kilometers, middle of nothing, you will find a lot of incredible number of hectares for juice product on orange, mandarin, and grapes. And what they do is not only to produce the fruits, they produce the fruits to make the juice. And they make the juice, and they want to export the juice, they concentrate the juice. And to concentrate the juice, they have to find a way. We learn how to concentrate the juice. That's what the patent they have in Australia. We're just using osmotic distillation or membrane distillation. But for doing this, you have a problem. And you learn that when you make membrane distillation, you want to increase. If you want to use normal technology at room temperature, you don't want to destroy the aroma, nothing from your wine or from your juice, you have to avoid temperature increase because you lose everything, you destroy all the aromatic part, etc. So you can clarify first, and after you go one of the technique, membrane distillation. But you know that in membrane distillation, part of the volatile are going with water. So if you have a delicate kind of bouquet, some wine, etc., you don't want to lose this. So what they're doing, here they introduce pervaporation. Because the pervaporation can just selectively remove, concentrate the aroma. And this aroma that you remove here, you will re-add after on the concentrate. So you can have exactly the same Cabernet Sauvignon, the same Chardonnay, etc., and that's what was real life for them. And you can separate here, and you can re-add after the concentration. That is, you enter with 18, 20 bricks, and you go out with 65, 70 bricks at the end. But the pervaporation can be utilized for solving this problem here. And some of these are just utilized. And what's important, if you do this, you can separate. You have to be quite accurate, and you will see how selective can be your membranes for some of the compounds. When you're talking about aroma, there is not a single compound. Aroma is a combination of 20, 30 different chemical compounds. So you need to have membranes that are able to separate at least the most important and the one that really contribute in positive to the final bouquet of your product. And that can be done, and each one of these membranes is doing his role. Okay, there are different this example if you want to spend time and doing some research, and that is interesting. Texaco, that is making this dimethyl carbonate. I was telling you with 70%, but that is a petrochemical company, big chemical company involved in this kind of separation. In China, they already have industrial plant also of the same kind. And this is some of the data of what is interesting, the comparison of the numbers. Traditional distillation, this is the number coming from Texaco, and this is the one that is the one if you operate with pervaporation. So quite interesting results. So you have a certain cost to replace your module that does not exist on the other side, but for the rest is quite competitive, and that's why they're using. And this engineering is also complicated. In any case, at least the one where we are measuring, you can see here, these overall operating costs are always beneficial. And if they are not, there is no slide to show. But normally when you see here, in this case, it's quite interesting that the overall cost at the end of the hybrid process, that means when you combine distillation and pervaporation, is competitive with the traditional one. And that is a lot of interest related to this potentiality in looking to different polymers that can be, or to different components that can be separated. That is nylon or celluloacetate, this adipamide and cellophane, etc. So people are still trying to investigate and to find something better, including, as we were discussing before, zeolite. And in some case, you see, it's not the traditional zeolite, but special one. Mordenite, for example. So it means that if you can find some specific kind of inorganic material with some specific selectivity that can be utilized for benzene paraxylane. This is quite interesting, very difficult to operate any traditional system, and mordenite is a special final morphology that can be of interest for this kind of separation. There is a lot of case study to be analyzed about new membranes, but just to give an example, polylactic acid is one of the interesting cases in which you can have separation for ethanol cyclohexane, which is one of the industrial cases. And this kind of polylactic acid is interesting also because polylactic acid at the end are just biodegradable. So it's one of the cases at the end, its membranes can be easily removed. And so this is polyactic, is a thermoplastic, aliphatic polyester, is obtained by a renewable source, that means starch or sugarcane, and biodegradable. And that makes all the overall system particularly interesting if you combine these properties with the one that is able to separate cyclohexane, hexane, etc. This is particularly of interest. That's why you can see here, these people are from Iran, and us, we are just using a traditional system. And for you that have to we have been learning that we don't have to prepare membranes. We have to prepare membranes appropriate for a certain kind of separation in terms of level of porosity for obtaining the separation, in terms of thickness for increasing or decreasing transmembrane flux, etc., etc. You can see here what you are supposed to do. Is if you have, for example, this kind of lactic acid, if you make a blend with PVP and you change PVP from 0 to 25%, you can see that you can significantly, the contact angle, so the level of hydrophobic or hydrophilic character, telling you if this membrane is hydrophobic or hydrophilic, can change significantly. You can go from 75, a relatively high level of contact angle, not yet hydrophobic, but approaching. Hydrophobic means from 85, 90 in contact angle, down to 45. So PVP is a way to make one material much more hydrophilic for the separation of your interest. And this is one of the effects. And okay, this is just a function of the amount of this. And the same is in terms of swelling. Swelling, I told you, is one of the important parameters because swelling is not just swelling. Swelling can be positive in the sense that means one of the components is penetrating the membranes and going across, and eventually the other one no. But swelling means a loss of mechanical properties. So you have to define very carefully the level of swelling and to combine the swelling with the stress strain, with the tensile strength, etc., to understand if this material can be also utilized at industrial level. So one of these problems is always to measure the swelling of your materials in the solution in which you are working. And depending from, you know, if you have to do something more, cross-linking, you saw the membrane that PVA can be, they are commercial, but they are cross-link membranes. If there were no cross-link, this membrane were not existing. And that will be just the measure of the degree of swelling. So this is one of the measures you always have to do before deciding if the system is working or not. And okay, there is a lot of this data in the literature, and we are still quite active in these things. And Dr. Figoli is the one that is preparing most parts of these membranes. He will maybe will be here in October and to discuss how to just realize some of these membranes in your lab. And it's interesting that you can have also selectivity, flux increase, selectivity increase, and we combine with this changing the flux. And that is something that the separation factor as a function of the membrane fluxes in this case, because it means one of the component is increasing its permeability and not the other one. So these things are just very much related. We don't have too much time, but just in case you will find your notes, there are 2 or 3 examples of some specific case of membrane preparation for specific membrane formation for specific separation. These were just examples related to the suggestion that you have to follow, that when you make a membranes, before starting to make membranes, you have to have clear in mind for which kind of application you are working and which kind of membrane operation you are working. Sometimes there is also in literature, people just make membranes. You take a polymer, because you have the polymer, you cast membranes, and after you measure its selectivity, etc. It's interesting, but that's not the right way of doing. You have to have clear in mind which separation you're looking for and which membrane operation you're looking for. If you decide that it's interesting to make pervaporation, you know that you have to produce dense membranes, eventually asymmetric, eventually composite, with very high selectivity for one of the components or for the other. Because you can, as you learn from slide number 5, in the same separation, you can use the same process, pervaporation, but you can make hydrophilic or hydrophobic. And you can separate one of the component or the other, and vice versa, changing the kind of membranes. And depending from the cost of the material, lifetime, mechanical stability, you can decide which one of the 2 approach you want to follow. And depending from the % of your component present in the feed solution, because to extract few ppm is much more interesting to extract all the 99% of the water, for example. In some cases that can be done, in some cases impossible. There are much more hydrophilic membrane than hydrophobic, for example. And this is a case that we've been discussing already. In some cases, this polymer is very, very flexible. As you know, PVDF we mentioned many times, but in our case we always mention polyether-ether ketone with this cardo group. That is a modified polyether-ether ketone. And it's interesting because the polyether-ether ketone is not soluble in any solvent, so you cannot use NIPS, TIPS, or the traditional phase inversion. But if you just make this chemical transformation, you introduce this cardo group, this lactone group. This lactone group is giving a lot of solubility in traditional solvents. And so this material is becoming easy to cast porous, dense, asymmetric membrane, depending what you want to do. This is the case in which we have been using this polyether-ether ketone for the methanol MTBA separation. That years ago was very interesting. So we're just making this, and you see here, this is a nice asymmetric membranes with a nice dense skin on the surface, with basically approaching hydrophobic characters. In 86 means, and if you want to make more hydrophilic, you can have just make more you have to make all sulfonation. If you increase the level of sulfonation, as some of you is doing for using this material for fuel cell, and if you want to increase the protonic conductivity, you make sulfonation, and that can be done. And so this number is going down or is going up, depending. And you can just try to find the separation factors, which is you have to measure, as I was mentioned before, swelling degree, and you can a function of the concentration of the methanol, and you have a level of swelling that is the interesting parameters, and that is just giving you the opportunity to decide. Also mechanical properties is the other testing that has to be done very quickly, because otherwise, if you have a membrane that is fragile, you can make publication, but you don't make any solution to the problem. And that's why you have to do this. And at the end, this is the tensile Young modules. You see that these numbers are quite, you have to do this kind of, you have to identify which polymer is the most appropriate for your kind of separation. And that is the case in which you are using polyimide or celluloacetate, etc., and you just are in an interesting range before immersion, and so you don't know what happened after all. Separation factor. These numbers are never too narrow in the distribution. Though you have a certain dispersion of the number, because this is not easy. Membrane can swell. You can change the thickness sometimes, etc. So you have to be careful in doing the experiment. But you can measure overall flux, which are quite interesting, and separation factor also at the end with membranes of this kind, and you can today find in the literature. Just to show that there is a lot of this new possible separation interesting, where pervaporation is tentative, one of the new technology to be tested. They don't exist, or they exist in literature, they don't exist on large-scale application, but for people that are able to synthesize new polymers, as you in this university, you can see that there is this kind of work where you can change separation factor from initial value to another content, just changing the percent of one component compared to the other is one of the things that can be done. And we can stop here and just summarizing that is interesting today more and more to have new resistant membranes with new material to face the new separation that are becoming important today. And the new separation, not just alcohol and water, are more and more organics, water, VOC, etc., in petrochemical industry, in a lot of different areas. So it's not, and you can find more and more other applications. We will continue on Friday, and we changed it with the program, discussing what I was mentioning, we were supposed to discuss today, membrane reactors. So from Friday we will just start with membrane reactors, okay? Thank you.